In this video, we'll continue to talk about functions, but we'll mostly talk about how we can get information from the graph of a function. So here's the graph of a function given to us, and we want to be able to read some input, output, pair information, domain, range, and then something else called the net change. So first, if this is the graph of h of x, then how do we find h of -2? Remember, the number inside the parentheses is the input, which corresponds to the x-axis. So I want to know what happens when x is -2. What y value does that correspond to? Looks like the y value is 1, so the output is 1. You might want to look at these, pause the video, try to figure out the next 3 outputs for the inputs that are given. H of 0 means find the output when the input is 0. And that looks like it's right down there at -1. H of 2 on the x-axis is about over there, so it looks like the y value is at about 3. And h of 3 is at about 4. Remember that for the domain of the function, we sweep in the horizontal direction along the x-axis. Think about as I move from -infinity to infinity along the x-axis, what points on the graph would correspond with the values on the x-axis? What x values do we get? So I also did this with a ruler. As we go through left to right, move along on the x-axis, where is the first point that I hit? It looks like it's right there at -3, and that's a solid point. There's no arrows here. It starts there, and then we keep hitting the graph for all values past -3 until we get to, it looks like 4, and there is a solid point there. Past that point, there are no points on the graph corresponding to x values. So the domain is the interval -3 to 4. Starts here, and you keep getting points until you get to here. For the range, we go in the other direction. We start from y values from -infinity and go up. Looks like the first y value we hit is right there at 1. And we keep hitting points on the graph with all the y values past that -1. The highest point that we hit is right there. So what y value is that? Looks like that's a 4. So the range is from -1 to 4. The next 2 questions give you the output because the number that you see is outside. So it's the output, and we're looking for x, the inside. We're looking for the input, so we want to know when h of x equals 3, that means when y equals 3, what x values does that correspond to? So when y equals 3, where do we hit the graph? Looks like we have a point right there, and there, and there. So what x values are those? Looks like we hit it at x equals -3 and at 2 and at 4. For what input values is the output equal to 5? Well, if I look at y equals 5 up here, does that hit any points on the graph? No. Remember, the highest it got was 4. So none. There are no x values that have that output. So the next thing is this definition, net change for a function on an interval from x equals a to x equals b is just defined to be f of b minus f of a. The change in the outputs. Where was the value at x equals a? Where is it at x equals b? What's the difference between them? That's what we call the net change of a function on an interval. So for this function h, now instead of the letter f, we have the letter h. We want the net change from x equals -3 to x equals 3. So on the interval from -3 to 3. That means I have to find h of the endpoint to the right minus the h of the endpoint on the left. Find those outputs and then subtract. So let's see, h of 3, we already know what h of 3 is. We did it up there. That's equal to 4. H of -3, I have to find. -3 is right here. The y value corresponding to that looks to be 3. So the answer is 4 minus 3 is 1. So you just have to remember this terminology. Net change means the difference between the y values, the change in the outputs. When we do application problems, this will make more sense why we even talk about it. Here's another example of two graphs given now. F is the red graph, G is the blue graph. And we are asked to first find which is larger, f of 0 or g of 0. Remember, 0 is the input here for both of those. The outputs are the y values. So f of 0 is the y value for the red graph when x is 0. Do you see where that is? Here's x is equals 0. That number right there is f of 0. I don't even have to know what its value is. I just need to know how to compare it with g of 0. So here's f of 0 right there. Now g of 0 is the y value for the graph of g, which is the blue graph, which is right here. Which one's bigger? When you go on the y-axis, the higher you go, the bigger the numbers. The red dot there is higher than the blue one. So in this case, f of 0 is bigger, is larger. What about f of -3 and g of -3? Again, the -3's are in the parentheses. They're the input. -3 is right here. F of -3 on the red graph is down there. G of -3 is up here. So which is higher? The blue one. G of -3 is larger. Again, as you go along the y-axis, the higher you go, the bigger, the larger the numbers get. Part C says, find the values of x where f of x equals g of x. Where do they become equal? For which x's are the y's equal? As you move along the different points on one graph, the y's change, the x's change. You move along the other graph, the x's change, the y's change. Where do they have the exact same x and y? That happens at the points of intersection. So what are the x values for those? At x equals -2, and looks like it's x equals 2. So where is f of x less than or equal to g of x? Remember, for the f of x and g of x are outputs. They're the y values. So where is the y value of the red graph lower, smaller y value means lower, than the y values of the blue graph? So think about as you move from left to right along the x-axis and you compare the y values, like when you're at -4. The y value for the blue graph is up here. The y value for the red graph is down here. So the blue graph is higher there. And at that point, f of x is less than g of x. And that trend continues as you move along the x-axis. The red seems to be lower than the blue until you get that x equals -2. and then that relationship switches. Then the red graph goes above the blue graph, so it gets bigger. And then that relationship changes again at the next point of intersection at x equals 2. Then G becomes higher than F. The graph of G is above the graph of F. So to answer this question, where is f of x less than or equal to g of x, is the same as saying, where is f lower than g? So we can see that that is and here. Now you have to be careful when you write your intervals. Your intervals have to contain numbers in the domain of both f and g, and because of the solid dots, there are no arrows here. There are certain start and stop points for each graph. So the domain of both of them seems to start right there at -4. And so between -4 and -2, the red is below the blue, so it's smaller. F is smaller than G. At -4 also, it's smaller, so we want to include that. At -2, they become equal, and equal is included in this inequality here, so we want to include that. And then between -2 and 2, the red goes above, so F gets bigger there. Then past 2 again, the G goes above, so F gets smaller. So we have to union this starting at 2, but we can't go all the way to 4 there. I had this highlighted here, but really I shouldn't have, because the graph of G stops at x equals 3. So we really should just go from 2 to 3. And we do include 3 because at 3, the graph of F is less than the graph of G. The next question is basically the flip side of that. Where is F bigger than G? F bigger than G means we want the graph of F to be above the graph of G. And that happens, starts at -2, but not including -2 because we want strictly bigger than. And then it stops at 2. So when you're comparing function values, you're really comparing the y values. Which graph is higher, which graph is lower. The higher the graph, the bigger the y value. Other properties of graphs that are important to us are what we call local maximum, local minimum, and then where the graph is increasing or decreasing. And this is pretty much common sense, what you can guess what it means. Local maximum is a point where the y value is the maximum, is the biggest of all of the y value of the points near it, the y's of the points that are near it, in its neighborhood, we say. So you can see as you trace along this graph, as I go along and trace along this graph, it's going up, up, up. When it's going up as we go from left to right, we say it's increasing. And then it starts to go down, down, down. So that point right there is where we have a local maximum, a local highest point. If we just restrict ourselves to just looking around that point right there, we have a peak at that point. So then after that point, it starts to decrease. And then right here at this point is what we call a local minimum. It's like a little dip, a little valley. When you look right around that point, it's the lowest point within that interval around it. And then it becomes increasing again. Then it has another peak. That's a local maximum again. And then it's decreasing. Then it has a local minimum again. And then it's increasing. And I don't see any dots there, so we're assuming there are arrows here. They go on forever. So first I'm going to actually write the local maximum and local minimum points. So you want to write just the ordered pairs for those points. There's a local maximum right here. And so the coordinates of that point are at -2, 3. And then there's another local maximum right there, which is at 1, 2. And that's it. Those are the only peaks in our graph. And then similarly, we have the valleys, the dips in our graph. There's one right there. That looks like the coordinates of that would be 1, 0. That's a local minimum. And then another one right there, which looks like it's at 2, -1. Now these are ordered pairs. Those numbers are the x and y coordinates. When we write the intervals of increasing and decreasing, remember to always write them as open intervals. Now this can become confusing with the notation because we're still using parentheses, but in one part of the problem, parentheses mean ordered pairs and points. In another part of the problem, parentheses mean open intervals. So just be mindful of that. So like we said, as we go from left to right, starting from -infinity, the function is increasing up to that x value of the first local maximum, which was at -2. And then it becomes decreasing, and then it starts to increase again at x equals -1 all the way up to 1. Did I say down here that this was 1? It should have been -1. I don't know if I said 1 or -1, but that should have been a -1. So we're increasing from -1 to 1, and then it's decreasing, and it's increasing again from 2 to infinity. For intervals of decreasing, we look at where as we go from left to right, the function, the graph is falling. So it's doing that from that first local maximum, which was at -2. It falls down to where x is -1. Then it starts to increase up to 1, and then it decreases again from 1 to 2. I want to point out again, there's a big difference between the 1, 2 that you see here and the 1, 2 that you see here. The 1, 2 here is an open interval. These are both x values from x equals 1 to x equals 2. In between those values, between 1 and 2, our function is decreasing. But the 1, 2 that you see in part C are is an ordered pair. Those are an x and a y value. It's a point 1, 2. In another video, I'm going to go over some calculator exercises with you to do some basic arithmetic and basic graphing on the calculator. And then we'll come back and do problems like this, graphing functions and finding their domain and range using our calculator, and answering questions about finding the local max, the local min, and intervals of increase and decrease. So make sure you watch that video also.